Okay, in a previous video I talked about how randomly polarized light bouncing off of a flat surface will cause most of the light to become horizontally polarized. However, however, it doesn't end up being totally horizontally polarized. It's just mostly horizontally polarized. Except there is a specific angle, Brewster's angle, that if the light comes in at that angle, it will bounce off and become perfectly horizontally polarized. So let's figure out what Brewster's angle is. If we have, here's our ray of light coming in, and we'll call this theta 1, or the angle of incidence, and it's hitting a barrier. Let's just, for the sake of argument, make this barrier air to glass. And then that piece of light is going to get refracted, and because the angle is, or because the refractive index is going from low to high, it's going to bend a little bit more towards the normal, and this is theta 2. The condition for Brewster's angle that will leave the reflected light all horizontally polarized is such that, I haven't drawn this very well, when the light comes in and bounces off, it has to make an angle of 90 degrees with the refracted ray. You know what, I'm just going to pause here for a second and see if I can draw this in a way that'll make it a little bit more accurate to what I'm trying to say. Let's just go back here for a second and go like that. And then we have this ray coming in. See, that was the problem, is I need to make that, Brewster's angle tends to be a little bit bigger. So there we go, that's better. This is, we said it was going to be air, so n equals 1. This is glass, so we have n equals 1.5. And again, going from a low to a high refractive index means that my ray is bending a little bit more towards the normal, and my reflected ray is coming out, and these two things, for it to be at Brewster's angle, should be at 90 degrees to one another. Now if we look at this, I'm going to expand this out a little bit, and we look at these angles. This is theta 1 and this is theta 2, and I'm just going to go through a little bit of geometry here to show you that if this 90 degrees is met, theta 1 plus theta 2 are going to work out to be 90 degrees. So let me show you that. So first of all, if I go from here to here, if that's theta 2, then this is going to be 90 minus theta 2. Okay? And then if I go from here to here, recognizing that this is 90 degrees, if this is 90 minus theta 2, then this right here is going to be theta 2. If we remember our law of reflection, theta 1 coming in and the ray bouncing back out, then this is theta 1 as well. And then finally, if I look at my last 90 degrees here, I can see my last 90 degrees here, theta 1 plus theta 2 have to add to 90 degrees. So that's just a bunch of angles. You can work through that slowly on your own if you want, but that's just a little way of showing you that if the refracted ray and the reflected ray are at 90 degrees to one another, then theta 1 plus theta 2 is going to work out to be 90 degrees. So with this secondary relationship, which is what's required for it to be at Brewster's angle, I can use Snell's law to then derive Brewster's angle. N1 sine theta 1 equal to N2 sine theta 2. Now, N1 sine theta 1 equals N2, and I'm going to replace theta 2 here with 90 minus theta 1. And then, I don't like 90 minus theta 1, so I'm going to exploit a trigonometric identity to get rid of that. So the trig identity I'm going to use here is sine A minus B, and that's going to be equal to sine A cos B minus cos A sine B. Because one of our angles is 90 degrees, this is going to work out nicely and simplify our expression. So what's nice here is I know that the cos of 90 is 0 and the sine of 90 is 1, So this whole expression just simplifies down to cos b because this term goes away. With that in hand, I can go back over here. Seeing that, I realize, I guess you probably could also, instead of using the trig identity, just recognize that this represents a horizontal shift of the sine function. So if I horizontally shift the sine function by that much and invert it, I end up with cos. But the identity, I think, is pretty easy to see. So I said cos b, but I should have said that 90 minus theta 1, theta 1, theta 1. In this case, b is theta 1, so this ends up being cos theta 1. Now I can move and get sine over cos, so I can simplify it to tan. And I get tan theta 1 is equal to n2 over n1. And that is an easy way to use the refractive indices of the two materials that make up the barrier of reflection to find Brewster's angle, or to find the angle where the refracted and reflected rays are at 90 degrees, and so the light will come off polarized horizontally completely. Let's take our specific case with glass and air, and we would say that tan theta b is equal to 1.5 on 1. And that works out to be theta b is 56 degrees. So that means if you were on a glass surface and you had a source of light that was shining down on you, and you looked at that light such that you were looking at it reflected from 56 degrees, you would get all horizontally polarized light coming back at you. Now, if you don't want to see that light, if that glare is a problem for some reason, you can exploit some vertical polarizers. And then that light will get blocked, and you'll only see light from other sources. You won't see the light that was reflected at that specific angle. So that's what's Brewster's angle. That's how you find it right there. Actually, there's your general equation right there. And if you want, there's the big derivation of that equation.